We were using the comparison test for positive values. Now, what if you have a series where the sequences that you're adding change plus or minus? It could be alternating. Alternating means it fits plus minus pattern. Or it could also be in different patterns, like plus minus minus, or some crazy pattern. I don't know. For that case, we have the absolute convergence test, which says if summation of absolute value of an converges, then the one without absolute value converges as well. It's a very simple thing. So here's an example. Does summation of cosine of n over n squared, n from 1 through infinity, converge or diverge? Well, cosine of n, all we know is that it's a value between -1 and 1, right? And it's quite random, almost random. Cosine 3, cosine 4, cosine 5. If you try to do that, it's really hard to track down the values. It doesn't follow a pattern that much. And because it's sometimes negative, you can't directly use the comparison test that we were talking about. So instead of trying to figure out the convergence of this, rather we're going to show the convergence of this absolute value.
How does that help us now?
Well, then we can use comparison test. Right? If it's positive, and if you have something that's bigger than this one, which converges, then this should converge as well. Right? Okay. So tell me whether, well, absolute value of n squared is just n squared. So this thing is really just absolute value on the top. Tell me another one which is bigger than this one.
Just an n at the bottom.
Just n squared on the bottom,
Without the
but
square.
what on the top?
1.
Oh,
1.
can you just like make it n cosine n over n? Or you want to get
No, cosine n over n, although you're right, it will be bigger than this one because you're decreasing the denominator. It's not going to be helpful. We want something that's easy enough that it's either like a p series or geometric series, so that you can come up with a conclusion. So you want to use 1 over n squared, because I know that cosine n can never be bigger than 1. So we know that. Okay. And summation of 1 over n squared, and from 1 through infinity, converges or diverges?
Converges.
Converges by p test. It's a p series with p equals to 2, right? So it converges because p test with p equals to 2 bigger than 1. So by comparison test, summation n from 1 through infinity of absolute value of cosine n over n squared converges. Oh, but then by the absolute convergence test says if the one with the version that has absolute value converges, then the one without the absolute value converges as well. By absolute convergence test, sigma n equals 1 through infinity of cosine n over n squared converges. Now, let's try to see why absolute convergence test works. Okay, so I don't want to give you the proof, rather I'll just give you some picture to think about. If you have something that's always positive and you're adding, I tried to give you this picture of summation of things are like jumps, right? If you're adding something positive, you jump right. You jump right. If you're adding something negative, you jump left, right? So if the absolute value version converges, that means you're always jumping right because you're always adding something positive. But as you're adding, the thing gets smaller and smaller in a very fast manner. It goes to 0 very fast so that the summation cannot exceed certain value. Right? That's what it means for something positive to converge. Right? But then if you take away the absolute value, that means some of these are negatives. So it might be like going twice like that, but then it's negative, and then you're going twice. But because your jumps are getting smaller and smaller, and even if you tried really hard, you couldn't go towards infinity. If you allow the signs to just change, it will just stay there. You won't be able to go far away. So that's why without the sum absolute value, it should converge. Okay? That's like the rough idea.